energy is a really powerful thing to know. It's really useful. Let me just make sure my thing is looking. Yeah, I think. Yeah, okay, that's fine. Okay, anyways, energy is a really useful thing to know. It's really powerful. And to start off with like this sort of unit review, I think it's really important to just try to conceptualize what even is energy. Before I start, I thought I'd just let you know, just so that you know I also follow the schedule. I'm gonna make my momentum video tomorrow. I'll do torque on Thursday, and I'll do rotational momentum on Saturday. And I know that's kind of late because I know we have a cumulative. Sorry, you can watch my other videos. And I'll do Unit 8 at the end. Yeah, I just wanted to say that just so that I know myself, like when to make these videos. I'm kind of behind on them. So, okay, energy. What even is energy? Energy is honestly really hard to describe. I think the definition our teachers gave us was really good. It's that it's like this substance-like quantity that causes change, right? In order to turn on your fan, it needs energy. If you want to break something, it needs energy. Or it takes energy. I'm honestly not too sure. Energy in physics, it has this whole field of study that I don't understand very well at all. In this class, or this, in AP Physics 1, we're really concerned about motion and how energy kind of impacts that. So let's actually take a look at like how energy is really useful. If we have a ramp like this, right, just your basic straight incline, right, and you can just have this, theta. You can figure out that, okay, there's an FG, right, there's the FG, X, right, and we could say that we can figure out like the final speed, right? We can do kinematics. Acceleration is equal to, G, you can do the math, G sine theta, and then you could do 1/2 AT squared equals change in X, and you can figure that all out. But in the real world, not everything's in ramps. You could get stuff like this, right? You can get, and I'll even make it a bit more, yeah, like something like this. If you want to figure out the speed that it's going at for this block, you can't just do kinematics, right? Like, this works because the acceleration is constant, but the acceleration is not constant here, right? Like, maybe right here the Fn's big, the force normal that is, right? And then maybe here it's like kind of small, and then maybe here it's super big. The forces constantly change, so the acceleration constantly changes. We can't just use kinematics. That's where energy comes in. What we can sort of, what's sort of going on, and if you take calculus, it'll sort of make, I guess, more sense to just think about. We could say that, hey, this object and the Earth has gravitational potential energy, therefore, at this point, if we set this is where h is equal to 0, and I'll talk about what all of that means, right? All the gravitational potential energy from this height is going to equal the kinetic energy, and we can figure out the speed like that. And it's not like oh, we're finding like an average. It is finding the exact speed. I had a kid, like, or a friend, Drew, shout out to you. He asked me like, oh, why does does doing mgh equals 1/2 mv squared, like that, like this finds the exact speed. Like, that's pretty cool. Like, it could be right here, it could be here, it could be here. You can find the exact speed based off its height. So that's really powerful to know, because you won't always have questions like this, right? You'll have a bunch of crazy situations. So yeah, energy is the ability to cause change. So here are some just important things to keep in mind in terms of like how can energy be stored in this scenario. So systems are important too, and I'll talk about systems as well. The object itself, right? So if you have a block, right? Maybe I'll draw that little scenario, just a mini version. You have a block. This block itself, just by itself, can store kinetic energy. So the block is going to have some kinetic energy. And now the equation for kinetic energy is 1/2 K equals 1/2 mv squared. And you can actually do an experiment and kind of see where this equation comes from. I think, maybe, I don't know. The point is, K equals 1/2 mv squared, if an object has mass and it's moving at a certain speed, keyword speed, and I'll talk about that a bit more, it'll have a certain amount of kinetic energy. Now, the block and the Earth. So this is like mainly for, like, you could say this for the block system, right? Now for the Earth, the block and the Earth are both gonna have, so like if this was a small, here, how do I draw this? So this is like a small section, right, on planet Earth. The Earth and the block will have a gravitational pull between them, an equal and opposite pole. And that pole is, I'll actually not talk about that yet. The block and the Earth are gonna have they're gonna have gravity, and this gravity, right, if it's over a certain height, we call that gravitational potential energy. So I'll say potential energy. And then we'll say that gravitational potential energy is UG equals mass times the gravitational field strength times the height. So this is for the block Earth system. Like, an object by itself cannot have gravitational potential energy. You need to include sort of both things in the system. You know, I think you could technically say, like, me and the eraser have gravitational potential energy. It's just very weak and not going to do anything, but it's there. So we'll say UG is equal to MGH. We're going to say block Earth system. These two right here are kind of your best friends. You will find this all the time. And then another one to keep in mind is also the spring. So the spring, or what do you call it? Elastic potential energy with springs. Potential energy. And then hopefully, if this is all boring to you, you can just skip through. U spring equals 1/2 kx squared. So it's really called potential energy because the energy depends on its position relative to another thing. So for example, the x here, that is the distance from the equilibrium. And we studied that in Unit 8, right? The distance from that equilibrium point. So that's what our stretch is. That's like our x. So the energy stored depends on its position. Same thing with gravitational potential energy. It depends on how high up you are from where you say h is equal to 0. And I'm going to actually talk about that right now. How do we use this to do like math problems? Like how is energy sort of used there? Well, there's this nice thing called conservation of energy. Energy is conserved. Like, the total amount of energy in the universe is constant. It's not going to change. So what you kind of have to realize is that, okay, if you had, let's just make this scenario bigger, right? Let's draw little pie charts. The energy here is going to equal the energy here, which is going to equal the energy here. So, all the energy is initially stored as UG for our system, our Earth block system. And then right here, it's all stored as K. And then right here, it's stored as like half, like let's say this is like half the height. It's not, but we'll just pretend. Half UG, half K. So what you can do is, you know that at any points, the energy initial is going to equal the energy final. This is a conservation of energy statement. We're just saying, hey, no energy is going to get lost, which is not always true, and I'll talk about that. Energy initial equals energy final. You have UG equals K, right? Let's say the energy here is equal to the energy here, which is also equal to the energy here. So I'll say UG initial, I'll say K initial, UG final, K final. You could say that these two are equal, you could say these two are equal, you could say these two are equal, like all three of them are equal with each other because no energy was lost. It's a very nice thing to sort of know, because it just helps us out so much. If I want to find the speed right here, I just do UG is equal to mgh plus or equal to 1/2 mv squared. Very handy. Just because now you just can find the speed there. I'm saying that a bunch. I just think it's really cool and really useful to do that. So yes. Now, this is something you gotta kind of realize is that system matters. And then for no matter what system you choose, energy will always be conserved. So let's kind of erase all this stuff here. Energy will always be conserved no matter what your system is. It has to be, right? If your system's a universe, the energy is conserved. And if your system is like an atom, like energy must be conserved. That's just a law of the universe. So let's say the system was only the block. Initially, and I'm going to bring back LOL diagrams. You don't necessarily need to know how to do them, but they're really handy. Hey, initially, it used to have all UG, and then it transformed, undo the O here, into all K. So UG, K. Okay, so we just set these two equal, but if the Earth is not in the system, this block cannot have UG. There's no, there's no potential energy stored gravitationally. It's not in the system, there can't be any UG. So the initial energy was 0, and then the final is going to be equal to 1/2 mv squared. This is impossible. I mean, if it's moving, this number is not going to be 0. How does this work? That's where, oh, hey, that's a nice little intro into it. Work. Work is a thing. So, all work is, and I'll kind of write this down, this is very important. Work is just a change in energy. That's all it is. My brother's screaming because he doesn't want to eat dinner. Sorry about that. Work is just, well, I don't know why I wrote area, change in energy. So, if there's obviously going to be a change in energy, right? It's going from 0 to K. So an additional force is doing work, right? Forces do work. So I'm going to call this, I'll call this Fg, the work by Fg. So the force of gravity of the Earth on the block is doing work. It's adding energy. So now instead of saying 0 is equal to 1/2 mv squared, we could say 0, which is the initial energy, plus the work done. So the work by force gravity is adding energy. The equation for work, this might not always work, especially not in this case, but the equation for work is going to be the force times the force parallel times this. Okay, I'm going to make this video later.